Hello again, welcome back. This video lecture, 8.3, goes with Chapter 8, Section 3 in our book, and the title of that section is called Reading a Potential Energy Curve. So we're going to need a little explanation as to what we mean by this potential energy curve, but I will tell you that in more advanced work in physics, this thing called a potential energy curve is used a lot. So we are at a perfect point in our development of the material to introduce this concept to you. And since it is so important in future work, we might as well go ahead and start the introduction now so that you can start to learn to understand all the important information that is contained in what's called a potential energy curve. A curve means a plot. We're going to be plotting the potential energy is what it boils down to, but I'll show you. So let me start with a key idea, first one we've stated already, and then develop it from there. And the key idea is the relationship between the work done by a conservative force and the change in the corresponding potential energy. That's this simple enough little formula right there. That's in fact the definition of potential energy. The work done by a conservative force, whatever conservative force it might be, is equal to the negative of the change in the corresponding potential energy. So we've applied that to, we've got two conservative forces, gravitational and spring. So the work done by the gravitational force is equal to the negative in the change of the gravitational potential energy. W grav equals negative delta U grav. Or the work done by the spring force is equal to the negative in the change in the elastic or spring potential energy. That's this statement. Now here's where we're going to start to develop that a little more. The next line in this chain of reasoning replaces the expression for the work done, W, by the general expression that we have used, first introduced in Chapter 7, for calculating the work done. We're assuming motion along one axis. Right now we're going to call it the x-axis, and that says to calculate the work done by a force F, you integrate the force f of x dx from x initial to x final. That is technically how you would calculate the work done by a force for motion along an x-axis. So we put that on the left side. And then we get, just rearranging it, this expression right here, which we'll use a lot in more advanced work. But it says, the change in the potential energy that goes with a conservative force can be calculated from the negative of the integral of the force dx from x initial to x final. It's a way of finding the potential energy change by integrating the force. We won't do that much on Wiley Plus stuff, not really, but we will do it a lot in more advanced work in other courses. Here's what we're going to actually do, though, in this class. All right, now here comes the next idea. It goes like this. If, according to this expression right here, if the change in the potential energy between 2 points, x initial and x final, can be obtained by the negative of the integral of the force, then from the fundamental theorem of calculus, which in a nutshell says differentiation and integration are inverse operations of each other. They undo each other. If the change in the potential energy is given by the negative integral of the force, then the force is given by the negative derivative of the potential energy. And this expression right here is the one that's useful for what we're going to do in our class. It says, for a conservative force, this is only valid for a conservative force, that the conservative force is equal to the negative derivative of the potential energy with respect to the coordinate on the axis. In this case, we've written it as x, assuming our particle is moving along an x-axis. That's pretty handy. You can get force by taking the derivative of the potential energy function, not with respect to time. Note, it's not a dt down here, it's a dx. with respect to the coordinate x. You could think of that derivative du dx as a spatial rate of change. It's not a rate of change with time, but a rate of change with space, position. And of course, there's that negative sign that we just have to live with. Now, remember the geometrical description of a derivative, slope of a tangent line. Well, the force is the negative derivative of the potential energy with respect to x. So here's the next big idea. If we have a plot of potential energy versus x, then the force is the negative of the slope of the tangent line on that plot. And that is very handy. Right? I say again, if you have a plot of the potential energy function versus the coordinate x, assuming it's moving along an x-axis, then the force is the negative of the slope of the tangent line, because derivative is slope of tangent. Let me apply this idea to the two conservative force functions that we know, the only two that we know, gravitational and spring or elastic. We'll do them one at a time. Let's do ugrav, the gravitational case. Now here, of course, the formula for the gravitational potential energy, ugrav, is mgy, and we assume a positive y-axis going upward with some origin somewhere that's been chosen. So here our coordinate is y. It doesn't always have to be x. It's whatever axis the particle is moving along. So here what we would sketch for our potential energy curve is ugrav on the vertical axis, and whatever the coordinate is for the axis the particle is moving along on the horizontal axis. In this case, it would be y. So ugrav on the vertical axis and y on the horizontal axis. And then the potential energy curve is just a plot of this function, m times g times y, where the m and the g are constants. So it's just linear in y, so it's just a straight line with a slope of m times g, which is positive, and 0 intercept. Like that. Okay? M, G, Y. That's the potential energy curve for the gravitational case. Okay? That's all it is. That's the potential energy curve. Now, apparently, it must be true that the corresponding force, gravitational force, is the negative of the derivative of the potential energy. So I'm going to take the negative derivative of ugrav with respect to the coordinate, which in this case is y. It's always going to be x. But it's not hard to take this derivative right here, the derivative of that with respect to y with m and g constant. We should be able to do that by now. We can't forget that negative sign, and we just get negative mg. Ah, the formula for the gravitational force with the negative sign meaning that the direction is negative y, i.e. down. Now that's all the potential energy curve says for the gravitational case. And in that case, since the potential energy curve is so simple, it's just a straight line, it's not that informative. It's a little bit informative, but not that much. So let's go on to the spring case, because that's the other conservative force we know. The spring case. Then the potential energy function, U spring, is 1/2. Little k, remember, is the spring constant, the stiffness of the spring, times the x coordinate squared. So here we're assuming our standard picture of a block and a spring on a horizontal x-axis. With the origin, x equals 0, the equilibrium position where the block would sit at rest. Let's sketch that. Let's draw the potential energy curve for the spring case. So now we plot U spring on the vertical axis and x on the horizontal axis, because our block, our particle, is moving along the x-axis in this case. X equals 0 is equilibrium. So now, of course, that plot, 1/2 kx squared with 1/2 and k constant, is just a parabola with its minimum at the origin opening up. Like that. It's my sketch of it anyways. Okay? That's the potential energy curve for the spring case. It's a parabola with the minimum at the origin, opening up. Let's then get the spring force from this. Apparently, the spring force can be obtained by taking the negative of the derivative of the spring potential energy with respect to whatever the coordinate is. Well, the coordinate here is x, so with respect to x. So here's the function right here. I have to take the derivative of that with respect to x, with the 1/2 and k is constant. Well, it's x squared. Derivative of x squared is 2x. Don't forget the 1/2 k sitting there. And so you get negative kx. Yes, when you do that derivative, that's just Hooke's law, the formula for the spring force that we already said. Okay? Note, by the way, you could even get a sense of that just by thinking of the slope of the tangent line to the potential energy curve. Think about the origin down there at the minimum of that parabola. The tangent line's horizontal there. Slope of that is 0. Slope of tangent in this case is force. The force is 0 when you're at equilibrium. Let's think about a point to the right of equilibrium, like there. There the tangent line is sketched roughly like that. That is a positive slope. But the force is the negative slope of tangent, so the force here will be a negative number. The force will be in the negative x direction, back towards equilibrium. If I'm to the left of equilibrium on this side, then the tangent line has a negative slope. But the force is the negative of the slope of the tangent, so the force is positive on this side, so the force is to the plus x direction, back towards equilibrium. So you can get a good sense of what the force is like just from the potential energy curve, even if it's a new potential energy curve for a force you haven't learned about yet. Let's practice with something like that. All right, here's an example of a potential energy curve, and we deliberately made it pretty complicated, not corresponding to any of the forces we've studied so far. Okay, and this potential energy curve is plotted for us. U in joules, look at the numbers going up the vertical axis, U in joules, versus x coordinate, where there are a few key places along x that are marked, x1, x2, x3, x4, and x5. And then the actual potential energy curve is that red curve. Pretty complicated. It's got a couple of regions where it's flat, and then it's got some curvature, and it's got 2 minima and 1 maximum. So that's pretty interesting potential energy curve. So here's the first thing I want us to do, and I want you to try this on your own. You can pause the video so you can think about it. But I want you to make a sketch of the corresponding force versus x plot. All right, if I plot force versus x that goes with this potential energy curve, what would it look like? And my hint to you is this formula that we just discovered. The relationship between a conservative force and its corresponding potential energy is that the force is the negative derivative of the potential energy. Okay, so pause the video and try to sketch for yourself what the force as a function of x looks like given this plot of potential energy. Okay, welcome back. I hope you tried this on your own. I'm going to show you now the potential energy curve and the corresponding force curve, and we're going to talk about it. Okay, the potential energy curve's in red on the left. That's the one I've shown you already. The force curve in blue is on the right. That goes with the potential energy curve. And it's all based on that relationship. The force is the negative derivative of the potential energy, so the force is the negative slope of tangent line. So to get the force graph on the right, all we wanted you to do was to think about the slope of the tangent line of the graph on the left. So for example, for x considerably less than x1 on the potential energy curve up here, see where I'm marking? It's flat. Potential energy curve is flat. Slope of tangent of a flat line is 0, so the force is 0 to the left of x1. That's right here. right? That's right there, 0 force. Then we go into a region roughly between x1 and x2 where the potential energy curves, whoops, I want that to be in red, where the potential energy curve slopes down. So the tangent line has a negative slope. But the force is the negative of the derivative, so the force value is positive between x1 and x2. And the slope of the tangent in there between x1 and x2 on the potential energy curve is changing some, so the force isn't constant, but it is positive. And so you get this region right here on the force curve, pretty large and positive. That means in this region of the x-axis, from a little bit to the left of x1 up until x2, in that region of the x-axis, we know we would have a large force in the plus x direction. Now when we get to the point x2 on the potential energy curve, right down there, we're at a minimum. So the tangent line is horizontal, and the slope of the horizontal line is 0, so the force when you're at the minimum of the potential energy curve is 0 at that 1x. It looks like it's at x2. Sure enough, on the force plot, when you're at x2, the force value is 0. That tells you this. Whatever particle is experiencing this conservative force that we're talking about here, if you put the particle very carefully at the location x2 and let go of it without pushing, it will sit there. Yes, because if you put it at x2, there's no force on it. Okay, now what happens between x2 and x3? Okay, let's look at the potential energy curve first. Well, between x2 and x3, the potential energy function is rising, isn't it? So the tangent line has a positive slope. But the force is the negative derivative, so negative slope. So the force is negative. That means it's in the negative x direction between x2 and x3. So sure enough, on the force curve, now between x2 and x3, the force is shown to be on the negative side of the force axis. That means if the particle is located between x2 and x3, the force on it is in the negative x direction. Okay, then we get to x3, right? Now x3 is at a maximum, or a local maximum, there on the potential energy curve. So the tangent line is horizontal. So the slope is 0. So at x equals x3, the force is 0. Sure enough, the graph shows, the force graph, that at x equals x3, the force is 0. So x3 is another location where, if I put the particle very carefully at x3 and do not give it any kind of a push, just let go, it will stay there. Although it turns out x3 is what's called a point of unstable equilibrium. So if it's sitting at x3 at rest, and you give it just the slightest tap to the right or the left, it will accelerate away from x3. All right, now let's look between x3 and x4. The potential energy curve now bends downward, doesn't it? So it has a negative slope. So the force is positive. So between x3 and x4, sure enough, it shows that the force curve is in the positive region. Now, back at x4, look at the potential energy curve. I'm at another local minimum where the tangent line is horizontal. So the slope is 0, so the force is 0. And sure enough, at x equals x4, the force passes through 0 again. And then what happens between x4 and x5? Well, the potential energy curve grows again, doesn't it? So the tangent line has positive slope. So the force is negative. So between x4 and x5, our force is in the negative region again. Then something interesting happens on the potential energy curve. At x5 and greater, the potential energy curve is flat again. Tangent line is flat. Tangent line has 0 slope. So the force is 0. And sure enough, for all x greater than x5, there's no force at all. All right, now here's what I want us to try. I want us to try a little practicing here, interpreting these graphs. Let's imagine the following scenario. We have an x-axis, Okay? And I'll start it at the origin, and we'll never go to the left of that, because we don't have any potential energy information to the left of the origin. And we're going to have a particle moving on this x-axis, and it's under the influence of this conservative force with its corresponding potential energy function. Let us imagine, I'll even mark x1, the special points, x1, x2, x3, x4, x5. Let's say we release our particle, there it is, we release it from point x1 from rest. Just put it at x1 and let go. It's going to be acted on by this force plotted here in the blue curve. I want us to be able to describe the motion of the particle after that. For example, if I put it at x1 and let go, will it just sit there? Will it stay? What will it do? Think about that a minute. Pause the video, think about it, and then come back. Okay, so what will this particle do if we release it from rest at x1? Well, let's apply this force curve with what we know from Newton. At x1, the force is pretty large and positive. So if I represent the force as an arrow, that'll be the direction of the force, to the right, plus x. So the acceleration will be to the right. So it's going to speed up, yes? In fact, it'll speed up for all the x region where the force is positive. That's between x1 and x2. So in that region right there, it speeds up. Then what happens after it passes through x2? Well, between x2 and x3, right, the force is negative. So I'll draw a representative force. It's not quite so big as it was before. Whoops, I meant to do that in green. But I'll draw it in the negative x direction, representing the force between x2 and x3. It's that way. So now the force is to the left, negative x. So the acceleration is to the left, negative x. But the velocity was to the right. So the velocity and the acceleration are in opposite directions. It's going to slow down. So in this region, between x2 and x3, where the force is negative, whereas before it was positive, the particle will be slowing down. So between x1 and x2 it speeds up, between x2 and x3 it slows down. All right, now let's look between x3 and x4. What happens? Well, between x3 and x4 the force is positive, isn't it? So now the force is back this way again. So the acceleration is to the right, positive x. So now it's going to speed up again. So between x3 and x4, it speeds up again. All right, what happens between x4 and x5? Well, between x4 and x5, the force is negative. So now the force is back this way. So the acceleration is in the negative x direction, opposite to the velocity. So in this region, it slows down. So it's like a whiplash. Here, particle speeds up. This region then slows down. This region speeds up. This region slows down. What happens once it gets to x5? Don't just say it stops, because what's the force after x5? There isn't any. So there's no acceleration after x5. If there's no acceleration, the velocity can't change, right? So after x5, v, the velocity, is constant. So it will just move, keep on moving in the plus x direction at constant velocity after that. Okay? So that's the story you can tell about how a particle will move. Really, all you had to be given to get to that story was this plot right here, the potential energy curve. Because from that, you could sketch the force curve. And from that, you could make this chain of reasoning that I did to draw my little picture below. Okay, so maybe hopefully you're starting to see how and why potential energy curves are useful in understanding the motion of a particle. All right, one more idea I want to bring up. Let's suppose our conservative force, just to make things simple enough or simple to imagine, let's suppose our conservative force is the only force doing work on our system. Then we know from the previous video lecture that the mechanical energy, E mech, of the system will be conserved. I'm assuming the particle is moving along an x-axis. So E mechanical will be the kinetic plus the potential, and the mechanical energy will have the same value no matter what where the location of the particle is on the x-axis. So E mech is a constant. But the kinetic energy and the potential energy functions, the U, the K, and the U, they will depend on x. But their sum, K plus U, which will be E mechanical, will be constant. That's what mechanical energy conservation means. Now you can use that fact and rearrange that equation and just solve it for the kinetic energy. K as a function of x will be the constant E mechanical minus U as a function of x, and then that can be used to help you find what the kinetic energy is at a given location. So I want to do just a little more practice with this same potential energy function, but I just want to add a little more information to it. Okay, so that's the same potential energy function, all right? U in joules, with the numbers going up on the vertical axis in joules. And the x-axis, for the axis our particle is moving along with x1 through x5 as special points. And there's the potential energy curve in red that we've talked about. All right, now let's say, like I said, that this is the only conservative force doing work, so the mechanical energy of the system is conserved. The mechanical energy will be constant. Let's just take a number just to have something specific. Let's say that our system has a mechanical energy equal to 5 joules. I'm going to add a plot of that mechanical energy on this graph. It's easy to do because the mechanical energy is constant. So when you plot it, it's just a horizontal line, a straight horizontal line. Here it is, right here. Unchanging value of 5 joules, right? See the 5? It's that number for all values of x. Okay, now we've added another form of energy on the diagram, haven't we? In addition to potential energy, we have mechanical energy. Now remember, by definition, E mechanical is kinetic plus potential. So now, at any given x value on this graph, how about right here? I just picked some arbitrary x. The potential energy value, U, is however high you have to go to reach the potential energy curve. So right there is a U for that x. Now you add to U K to get E mech, but E mech's up here at 5. So you just go straight up from the potential energy curve until you get to the mechanical energy line. And that part that I just drew in purple represents K, kinetic energy. Because kinetic plus potential must equal 5 joules for any x. So the point is that you go up from the x-axis until you hit the potential energy curve, that's U, and then the rest of the distance you have to go up until you hit E mech, that's K. And so you can just look at this diagram now and see how the kinetic energy changes as the particle's x changes. What if the particle is at, let's pick a different location. What if it's at x4? Right here. Then this is how much potential energy it has, however high that is. And then from there up to the mechanical energy line, that's how much kinetic energy. So that much is potential, and that much is kinetic. Okay? All right. What about if we're over here to the right of x5? How about an x value right there? How much kinetic energy would the particle have there for this diagram? Well, go straight up till you get to the potential energy curve. That's U. It's pretty clear, isn't it, from that diagram, graph, that that's 4 joules. And then the rest of the distance, until you get to the mechanical energy line, is the kinetic. Well, if I went up 4 joules and the mechanical energy is at 5 joules, then the kinetic energy is 1 joule. So from x5 onward, the particle's kinetic energy, in this case, is 1 joule, and its potential energy is 4 joules. And its mechanical energy is 5 joules. All right, here's a question for you. Where on the x-axis is the kinetic energy of our particle, for this case, our particle with 5 joules of mechanical energy? Where is its kinetic energy the biggest? At what x value? Can you see right? You should be able to see right from the graph. Where is the greatest distance from the potential energy curve to the mechanical energy line? Right there. Yes? At x2. That's where the kinetic energy is the biggest. In fact, it's 5 joules. All of the mechanical energy is kinetic. Where is the kinetic energy the least? This one's a little more subtle. The answer is at x1. Something rather special is happening at x1. At x1, the potential energy curve itself intersects the mechanical energy line, doesn't it? That means I have to go all the way up to 5 joules just to account for the potential energy. But the mechanical energy is at 5 joules, it's also. How much is left over for kinetic in this case? None. Right? The particle, when it's at x1, for the instant it won't stay there, for reasons we already know from the previous slide. But when it is at x1, for that moment, its kinetic energy is 0. It will be at rest. Now, here's an interesting question. Why do you think the mechanical energy line is drawn to the left of x1 as a dashed line? See it here? What is that supposed to represent? What is that trying to say? What it's saying to you is that you will never find the particle. If its mechanical energy is 5 joules, you will never find it in that region to the left of x1. Why? Because if you are to the left of x1, your potential energy is more than 5 joules, but your mechanical energy is 5 joules. So to make that all come out right, you'd have to have negative kinetic energy. But the kinetic energy formula, 1/2 mv squared, can never be negative. So this region, in this case, to the left of x1, you will never find the particle located there. That's assuming its mechanical energy is 5 joules. That region is said to be classically forbidden. So there's a lot of information in a potential energy curve, especially when you add the mechanical energy line on top of it. And there'll be some Wiley Plus homework on that. Okay? And I hope that this video lecture is helpful for you in interpreting that. We're just getting started with potential energy curves in this class. They'll be showing up again and again and again in other classes. But I'm going to leave you with this video with a class engagement exercise that you will answer on Blackboard. That involves interpreting a potential energy curve. I will just read it to you, and then you will go into Blackboard for this video lecture 8.3, and you will type in your answers. So we're given another potential energy curve, in this case, U of x in joules. And you can see the diagram's made up of discrete line segments. Okay? U in joules as a function of position x. So our particle is moving in a one-dimensional x-axis. And we have a series of questions about this diagram. Question 1, rank the three regions of the x-axis, A to B, B to C, and C to D, according to the magnitude of the force on the particle from greatest to least. That's question 1. Question 2, what is the direction of the force, plus x or negative x, when the particle is in region AB? If the force is 0, then just say the force is 0. Question 3, what is the direction of the force, plus x or negative x, when the particle is in region BC? If the force is 0, just say that. Question 4, suppose the particle has a mechanical energy, E mech, of 1.5 joules. What is the particle's kinetic energy in joules when in the middle of region BC? And question 5, suppose the particle has mechanical energy E mech of 1.5 joules. Will you ever find it at point A on the x-axis? That point right there. Yes or no? Okay, those are the class engagement exercises that go with this video lecture. And there will be another video lecture coming up here in a little bit, but for now, that's all for this video.